Hello everyone, I'm your instructor, Wang Shengdao. Today, we will study configuration in polymer chain structure. Through this lesson, you will learn about linkage isomerism, geometric isomerism, and optical isomerism in polymer chain structures, as well as their influence on the properties of polymers. You will also learn to identify linkage isomerism, geometric isomerism, and optical isomerism, and strengthen your ability for active thinking. Configuration refers to the spatial arrangement of atoms in a molecule that is fixed by chemical bonds. It mainly includes three types: linkage isomerism, geometric isomerism, and optical isomerism. Let's begin with linkage isomerism. First, let's look at a concept, linkage structure, which refers to the way in which repeating units are connected within a polymer chain. In addition, polymerization for symmetric monolefin monomers, such as ethylene, the polymer polyethylene has only one type of repeating unit connection. However, for asymmetric monolefin monomers, there are two possible linkage structures. We refer to the carbon atom attached to the substituent R as the head, and the carbon atom without the substituent R as the tail. When the head carbon atom of one repeating unit connects with the tail carbon atom of another repeating unit, the structure is called a head-to-tail linkage. When the head carbon atom of one repeating unit connects with the head carbon atom of another repeating unit, the structure is called a head-to-head linkage. Similarly, we can also have a tail-to-tail linkage. Different linkage modes of repeating units result in different polymer properties. For example, in polyvinyl chloride (PVC), most repeating units are connected in a head-to-tail fashion. However, head-to-head linkages can lead to photochlorination reactions under sunlight, forming double bonds in the polymer chain. This causes PVC aging. Therefore, the more head-to-head linkages present, the more easily PVC undergoes degradation. Next, let's study geometric isomerism, also known as CIS, trans-isomerism. This type of isomerism occurs when the two carbon atoms of a carbon-carbon double bond are each connected to two different atoms or atomic groups. For example, in 2-butene, when the two methyl groups attached to the carbon-carbon double bond are on the same side of the double bond, it is called CIS-2-butene. When the two methyl groups are on opposite sides of the double bond, it is called trans-2-butene. Let's take poly-1,4-butadiene as an example to understand how geometric isomerism affects polymer properties. In CIS-1,4-polybutadiene, the two methylene groups in the repeating unit are on the same side of the double bond. The distance between molecular chains is relatively large, and the polymer is an elastic rubber at room temperature. In trans-1,4-polybutadiene, the two methylene groups are on opposite sides of the double bond. The molecular chains are more regular and can easily crystallize, with poor elasticity at room temperature. Cis-butadiene rubber refers to CIS-1,4-polybutadiene. Finally, let's study optical isomerism. This type of isomerism arises when a carbon atom is bonded to four different atoms or groups, forming a chiral center. As shown in the figure, although the two molecules have the same composition, they actually represent two different structures. Optical isomerism is also known as chiral isomerism, because a pair of optical isomers are mirror images of each other, like human left and right hands, but cannot be superimposed. Let's take polypropylene as an example to see how optical isomerism affects polymer properties. Isotactic polypropylene, also called isotactic polypropylene, is composed entirely of repeating units with the same optical configuration. Its molecular chains are regular and can crystallize easily. The polypropylene commonly seen in daily life is isotactic polypropylene. Syndiotactic polypropylene, also known as syndiotactic polypropylene, is composed of two types of optical isomeric units linked alternately along the polymer chain. Its molecular structure is also regular and can crystallize, and it has been produced on a small industrial scale. Atactic polypropylene is formed by randomly arranged optical isomeric units. Its molecular chains are irregular and cannot crystallize. It is mainly used as a hot melt adhesive, paper coating, or asphalt modifier, among other polymer additives. In this lesson, we learned about the concept of configuration, including the definition and formation of linkage isomerism, geometric isomerism, and optical isomerism, as well as their influence on polymer properties and applications.